Hey, today we're here to discuss radiometric dating, which as opposed to relative age dating actually puts an age on a substance. So we're going to do a chemical analysis of an object to figure out how old it is in years as opposed to relative to the position of something else around it. So let's dive into it. How is radiometric dating used? How is it done and how does it work? Those are our three questions today. Start off with some basic chemistry though. We'll go out of this a little bit, come back into the dating. So of course an atom, here's an atom of gold, okay, has a nucleus with protons and neutrons surrounded by electrons orbiting it in various configurations. The atomic number, okay, of gold here is 79. That's the number of protons in the nucleus. The atomic mass, this number, is the sum of the protons and the neutrons together. Now, sometimes you get isotopes of certain elements where you have two atoms of the same element with different numbers of neutrons. So they have different mass numbers. Okay, so what does that mean? Isotopes are unstable. They're going to undergo radiometric decay. So they emit radioactivity. So in these isotopes, the nucleus is unstable and will spontaneously break apart. One of the types of radioactive decay is alpha decay. And in alpha decay, you actually emit an alpha particle, which is essentially equivalent to a helium atom. And the mass number of the element will drop by 4, and the atomic number drops by 2, so it actually becomes an entirely new element. Now, in electron capture, a second method of decay, the nucleus captures an electron, which combines with one of the protons in the nucleus to produce a new neutron. So the element's the same, the mass number stays the same, but the atomic number decreases by 1 because there's one less proton. So again, it becomes a different element. I was almost getting this mixed up with beta decay. Beta decay, an electron is emitted, leaving the mass number unchanged, because electrons don't really have a whole lot of mass. They do have some, but not a lot. It means the atomic number increases by 1. So it still becomes another element. So in each form of radioactive decay we talked about here, a new element is created through the decay process. Now some of these elements decay through a whole series until they get down to something stable, but we're not going to get into that really. We're just going to jump and talk about dating here a little bit. As a percent of parent isotope, that's the original isotope, decreases. The percentage of the daughter isotope increases. The ratio of those two is used to determine the age of a substance. A key component of this is understanding what a half-life is. The half-life is the time required for half of the parent nuclei in a sample to decay to the daughter nuclei. And I give you this silly example. You can pause it, read over it, and see what you think. But basically, after one half-life, 50% of the parent remains and 50% of the daughter exists. So it's a 50-50. After two half-lives, it's 75% daughter, 25% parent, and so on and so forth. I'll show you a graph of this here in a moment. Using carbon-14 dating as an example, carbon-14 dating is used to date events of the last 50,000 years, or objects made or deposited within the last 50,000 years. It has a 5,730-year half-life. It's produced naturally in the atmosphere through cosmic rays. So all organisms, even humans, you and I, contain carbon-14. It's a form of beta decay. Decays of beta decay. That's terrible. Decays through beta decay. So you start out with carbon and you end up with nitrogen. So you start with an unstable carbon. Stable carbon's carbon 12-6, but here's 14-6. And you end up with a stable isotope of nitrogen, and then it stops. So the mass actually increases by 1. Here's an example of a decay curve. So here's the parent isotope, starts out at 100%, daughter starts out at 0. Daughter, the red line is nitrogen, the blue line is carbon. As the carbon decays and decreases, the nitrogen accumulates and increases. At this point, right where they cross, that's one half-life, 5,700, well they say 5,715, 5,715, 5,730, close enough. Bottom line is that's one half-life. Two half-lives, for two half-lives you have to go out a little further. So there's 11,430 years, okay, and so on and so forth. Some useful isotopes for dating. Radiocarbon's great for young things, but if you're going to talk about rocks, it's not all that useful. So you have to use things that have a little bit longer half-life. And these are in the case of these, you've got one that has a half-life of millions of years, and then most of them have billion-year half-lives. But you start out with the unstable isotope, and you end up with the stable isotope. Okay, time for a game. Go to this website and check it out. You can leave this up if you want, if it's helpful. Pause it here and open a different tab or something. But I give you directions for each of the little tabs in the game. Have fun. We'll probably do this in class as well as a demonstration. But go ahead and do it on your own. Till next time.